Right, so the intermolecular forces are going to affect the physical properties of these different substances. And we're going to look at a few of these properties, starting with, I believe, viscosity. Yes. So when we're looking at viscosity, resistance of a liquid to flow. So if you think about something like maple syrup versus water, the water is going to flow much more easily because the maple syrup is going to have a higher viscosity. And with this viscosity, we're going to see that the viscosity is going to increase. So the resistance to flow is going to increase when we decrease the temperature. Because we're going to be slowing down those molecules, the intermolecular forces are going to be stronger, and then just stronger within that substance. But also we're going to see that the viscosity is going to increase when we've got substances with stronger intermolecular forces, because in that case, what we're going to see happen is that those substances are going to be more attracted to one another. They're not just going to flow as easily. So if you look at the alkane series here, so hexane, heptane, octane, nonane, decane, we're just adding an additional carbon each time. And then these are going to be non-polar substances just because they're going to be the carbon chains just with hydrogens on the outside. But the reason we're going to see the viscosity increase, so you go from 10 to the negative fourth to 10 to the negative third, as we have 6 carbons to 10 carbons, is going to be because we're going to have that strong or an increased amount of dispersion force there. So those molecules are going to be more attracted to one another. They're not going to flow as easily because of that. And another property is going to be surface tension. So you can see the picture on the right here. There's some sort of bug that's actually able to essentially just stand on water. And it's going to be due to this phenomenon known as surface tension. So if I can get the draw thing. So with it, when we look at a liquid like this, where I've drawn this line, I've kind of got one top layer here, and then the rest at the bottom are separate. Because when we're looking at a liquid, we've got kind of 2 different aspects of it. One of them, the bottom one here, is going to be known as the bulk. And if you look at this one molecule in particular, so if we think about each of these circles as representing a water molecule, with the water molecule here in the middle, it's going to be attracted to water molecules in every direction. Whereas if we go to the surface now, in this case, they'll be attracted to molecules on the side as well as molecules on the bottom, but there's nothing going to be above it in order for it to be attracted. So what we're going to see is with the surface molecules, they're going to have a net force pulling them down. And what that's going to do is allow these top molecules to actually get sort of pulled closer together, and they're going to have a better arrangement. And that's why we're going to see the surface tension here occur. And then with it, we're going to see that the surface tension is going to increase with the intermolecular forces as well. So if you've ever seen water, if you fill up a container or something, water isn't just going to stop at the top and then fall off the sides. It's going to have that surface tension. So you're actually going to see it kind of create a bubble almost on the top. And it's going to be because those water molecules are going to be attracted to one another. And that's why we're going to be able to, if this beaker was completely filled, it's going to be able to get filled to actually above that brim, just because the surface tension there. And then with the surface tension, oops, let me get rid of that mark. This is going to be the supporting idea, or what actually occurs in what are known as shot towers. So if you look here, it's just a tower, and what they would have at the top is molten lead. So we're just going to have the liquid lead. And then there's going to be a sieve that's going to be able to create them into circular or spherical pieces. And then what's going to occur is what's going to happen is they'll fall down to the bottom. And then during that fall, they're going to cool down, they're going to solidify. And then finally, there's just a cooling pool to get them fully cold, just filled with water. And the reason this is going to work is as they're falling, they're going to be in that spherical shape from the sieve. And then those outer molecules are going to have that surface tension. They're going to get pulled in by the inner molecules, and that's going to allow them to keep that spherical shape. So because there's nothing on the outside sort of pulling on those molecules on the surface, they're getting pulled inwards. That's why we're going to see the spherical shape occur. And then with it, you can kind of just see some of them here. There's some sort of system they have. So if there's a defect or something, they can basically just remelt that lead and use it again. But you can see the picture here again. We're going to have the liquid metal, and then it's going to cool as it falls. But because of that surface tension, we're going to wind up with spherical shock. And then based on the size of the sieve, based on the height of the tower, that's how they can get different size shot. But with the intermolecular forces, those are going to be what we're changing whenever we have a phase change occur. So if we go solid, liquid, liquid to gas, gas to solid, any of these processes, we're not going to be changing the intramolecular forces. So we're not going to be changing the covalent or the ionic bonds within a single molecule. We're just going to be changing the intramolecular forces between those different molecules. And with it, we're going to see that it's going to require energy. So if we think about intermolecular forces as a cohesive attraction, they're going to help keep things together. We can think of kinetic energy as a disruptive force, and temperature is just going to be a measure of average kinetic energy. So as we heat something up more and more, we're going to have more and more kinetic energy. And eventually that kinetic energy is going to become enough to overcome those intermolecular forces. And that's going to be where we see a process like vaporization occur. So with these phase changes, we just want to keep in mind that the changes themselves are only going to be impacting the intermolecular forces. And when we look at the energy of this process, like I said, it's going to take energy to actually separate these molecules. And once the kinetic energy overcomes those intermolecular forces, that's where the phase changes will occur. So if we look at it here, we've got butane, diethyl ether, water, and mercury. And with it, butane, it's just going to be an alkane, so it's going to be nonpolar. Diethyl ether, you can kind of see the structure here. So an ether is just going to be an oxygen that's got two different carbon chains on the outsides of it. And in this case, diethyl just refers to two carbon chains that are each 2 carbons long. This is going to have dipole force, dipole-dipole interaction, because it's going to be a polar molecule. Whereas water is going to have hydrogen bonding just because we've got the hydrogen bonded directly to the oxygen. And then mercury is going to be nonpolar, but it's going to be a very large atom. So when we look at the intermolecular forces, or the heat of fusion, I should say, which is the energy needed to change it from a solid to a liquid, so the energy to melt it essentially, we can see a gradual increase in the heat of fusion. And with it, part of the reason is going to be water is the smallest. So even though it's got hydrogen bonding, it's going to be smaller than the rest of these. So these will have higher dispersion forces, particularly with mercury. And then when we look at the heat of vaporization, now we can really see the trend we'd probably expect. Because again, we've got dispersion force, dipole-dipole, hydrogen bonding, and then really large dispersion force here. But what I want to focus on more than that is the relative changes between the heat of fusion and then heat of vaporization, which is the same thing. It's just now instead of looking at solid to liquid, we're looking at liquid to gas of vaporization, essentially creating a vapor. When we look at the heat of fusion versus the heat of vaporization, we're going to see vaporizing a substance is going to take much more energy than the melting process will. And if we think about the intermolecular forces, that kind of makes sense. Why? Because going from solid to liquid, we're going to be weakening those intermolecular forces, but all of those molecules are still relatively close together. That intermolecular force is still going to be relatively intact. But then when we go from liquid to gas, now we're completely separating those molecules, or they're essentially independent of one another. So we're completely sort of dismissing the intermolecular force, and that's going to take a lot more energy to actually separate those molecules completely. And that's why we see heat of vaporization much higher than the heat of fusion for these different substances. It's going to take a lot more energy to get it into the gas phase than it is to get from solid to liquid. And we can also look at these phase changes with what are known as heating curves. So in this case, we're looking at an entire heating curve. And this is going to be for water, so that's why these lines are going to be at 0 and 100. Excuse me. But with it, we've got kind of different segments of this heating curve, and it's not really a curve in the sense you'd expect, like a curved line, but it's just what we call these. But with it, we've kind of got different segments to it, and some of these are sloped, some of them are just flat. With the sloped ones, if we look at the axes, temperature on the y, heat added on the x. With the sloped ones, these are going to be where we actually see temperature changes occur. And of course, it makes sense. We're going to be adding energy while we do it. But these are going to be where we have the pure states of matter. So at the bottom here, our lowest temperature makes sense. It's going to be solid. Middle one, liquid. Top one, going to be the gas at the highest temperature. And then what we have on the flat sections are just going to be those phase changes themselves. So that's why with water, if we're thinking about 1 atmosphere, it's going to melt at 0 degrees, going to melt at 100 degrees. And even though we don't have a temperature change occurring, so it stays flat at 0, stays flat at 100, what we're doing is changing those states. So going from solid to liquid, B to C here, or liquid to gas, D to E. Even though we're not changing the temperature, this is still going to require energy. And that's what we're going to be looking at with the heat of fusion for melting and heat of vaporization for the boiling process. And then when we're trying to calculate exactly how much energy this is going to take, we've got a couple different equations. 2 of them look the same. And then with these 2 at the bottom, Q, I should say, is going to be for the heat. With these 2 at the bottom, how I have it set up now is mass times heat of fusion or heat of vaporization. So how much of that substance do we have in grams times whatever the heat of vaporization or heat of fusion is going to be for that substance. But you can also see essentially the same equation with moles out in front. So it can be N instead of M. And with it, we just have to pay attention to what the units are on vaporization and fusion here, the enthalpies of vaporization and fusion. If it's kilojoules or joules per mole, then we would need moles here. If it's joules per gram, then we would need grams here. So we just have to pay attention to our units. But there's no temperature unit in this one because they're just flat. So it's just going to stay at whatever that temperature is as we change the state of matter, which is going to require energy. It's going to require heat. But then when we do have the temperature changes occur, where we're looking at one of these flat sections, now we'll have the mass of the sample. So how much of it do we have? C is going to be the specific heat. And then the temperature change, how much is that temperature changing? So with temperature, with the delta T, just remember delta anything is going to be final minus initial. So in this case, if we're looking at the temperature change for the liquid phase, 100 minus 0, because we're having 100 increase in temperature. If we were cooling it, then we would have 0 minus 100. So we'd have a 100-degree decrease in that case. So it's always final minus initial. And then with the specific heat here, that's going to be in joules per gram degree C, because that's going to tell us how much energy is needed to heat 1 gram of that substance by 1 degree. And if we've got joules, I can write this. If specific heat is joules per gram degree C or Kelvin, because it's going to be temperature, delta temperature. It doesn't matter if it's Celsius or Kelvin since they're the same scale. But if that's a RC, we've got mass in grams. We've got delta T in degrees C. That's why we're just going to be left with joules here. So that's going to be our energy unit for heat. And then with the specific heat, if you think about it, typically metals are going to have very low specific heat. That's why they heat up and cool down very quickly. Whereas water has a relatively high specific heat. And that's important environmentally just because water helps regulate the air temperature. So here in Washington, it doesn't get as cold or as warm in the winter, the summers respectively, as it does in the middle of the country where they don't have the water to regulate the temperature. And that's going to be because of the specific heat of water. It's going to take a lot of energy to either heat it up or cool it down relative to water, or not relative to metal, excuse me. And that's why if you heat up a pot for pasta or something, the pot itself is going to heat up much quicker than the water will. I thought I put these in. Oh, okay, cool. So if we look at a question like this is actually going to be asking how much energy is needed to heat 100 grams or 1 mole of water rather from the heating curve we had before. So if we look at this curve, negative 25 degrees Celsius up to 125 degrees, that's what this question is going to be asking. So 1 mole of ice at negative 25 degrees C to water vapor at 125 degrees C. Because they're saying constant pressure, heat, so Q is going to be equal to delta H. So we don't have to worry about really complicating this at all. We'll just be able to use these equations. But with it, since we're going to be going on 5 different segments of this heating curve, we're essentially going to have to do 5 different little calculations because we're going to need to determine how much energy is needed to heat the ice from negative 25 to 0. Then we're going to need to figure out how much energy is needed for the phase change, energy needed to heat up the liquid, energy for the second phase change, and then the last little bit of energy to heat up the gas there. And when we're looking at it, we can use the vaporization equation and fusion equation for these phase changes. And then we can use the MCAT equation for the temperature changes. But with this one, we're going to have a different specific heat for each of these different phases. So it's going to take a different amount of water, different amount of energy, excuse me, to heat up 1 gram of water by 1 degree, depending on what phase that water is actually in. So if we look at it, 2.09 joules per gram Kelvin for ice, double that for water, liquid water, and then 1.84 for the steam. So it's going to take less energy to heat up steam than it will be the liquid. And then with the delta H for fusion and vaporization, in this case, it's in moles. It's also in kilojoules. So what we're going to need to do is convert those units to match up. And with 1 mole of water, that's going to be 18.02 grams. So we can use the grams for the ice, water, and steam. We can use 1 mole just for the heat of fusion and heat of vaporization. But we're going to need to change the kilojoules to joules, just so that when we add up these different pieces, they actually can be added up. So when we look at it, this is the main equation we're going to need, or the total equations we're going to need, because we'll have a different one for each of those segments of the graph. And with it, for the first one, 18.02 grams, since it's 1 mole, specific heat of the solid. And then we've got a 25-degree change. So 0 minus negative 25 is really just positive 25. And then we've got different pieces for each of these other ones. For the heat of fusion and heat of vaporization, since it was just per mole and we have 1 mole of it, I just simplified it and just put joules here. So I just didn't really include the calculation for it, but it's just multiplying by 1. But with the liquid and the steam, just like with the first one, we've just got the mass times the specific heat for whatever phase we're in, and the temperature change for that phase as well. So if we ever have a question like this, what I would recommend you do is just go back, and even if you have to kind of sketch one out yourself, just draw a little heating curve like this so you can identify where we're starting, where that phase change is going to occur, and then how much more we're either going to be heating it or cooling it. And then for however many of these line segments that you have, that's going to be how many of these different little equations that you're going to need to string together. And then for this one, we rounded it just to 56.0. But if we look at the temperature here, this really only has 2 sig figs in it. So it really should just be 56, just even. And then with the next one, kind of a similar question, but in this case, we're going to be cooling a substance. So we've got 100 grams of water and it's starting at 50 degrees C. So it's going to be liquid water to start. We're going to cool it down to negative 30. So we're going to have 3 different segments of this, in this case, cooling curve rather than heating curve. But we're going to have 3 different segments of it. So we're going to need 3 different pieces of our equations strung together. And the first one's going to be figuring out how much energy is released in this case from cooling liquid water from 50 degrees to 0. Then how much energy is released with the phase change going from liquid to solid. And then the same thing, cooling it down from 0 degrees to negative 30. So if we look at the setup, we can essentially eliminate heat of vaporization and then this final MCAT equation, because we'll just have the heat of fusion when we have the liquid to solid phase change. and then 2 of the temperature changes. And with this one, there's a couple different ways you can plug it in. With the temperature change ones, just remember final minus initial. So 0 was our final temperature for the liquid. It started at 50, so 0 minus 50 gives us a negative temperature change. It's going to give us a negative amount of heat because we're going to be releasing it from the system. And then with the other cooling one, same idea, negative 30 is our final, 0 is our initial in that case, so negative 30 minus 0 gives us negative 30 degrees. But with the phase changes when we're cooling it, what you could do is just make the plus sign between these different little equations. You could just make that a negative. But what I typically do is just take the heat of fusion or the heat of vaporization, depending on which change it is. In this case, heat of fusion, because we're liquid to solid. But I usually just make that a negative, just to make sure that we account for the sign here. Because in this case, we're going to wind up with 3 negative pieces of our equation, just because we're cooling the substance down. Where the first one we looked at, we were heating it up. So that's why we had positive numbers for all of these different segments that we had. And in this case, what we're going to see is it's going to release it's negative, or it's going to release 60.5 kilojoules. So that's why we've got the negative sign there. And then with vapor pressure, we kind of already talked about this in the gases chapter, but vapor pressure is just going to be the force exerted above a liquid in its pure state. Doesn't even have to be in its pure state, but it's just going to be the force exerted by a substance above its liquid, or it could even be a solid in some cases. But what we're going to see is the vapor pressure of a substance is going to increase with the temperature, because the higher the temperature, the more kinetic energy those substances are going to have, those molecules are going to have. So more of them are going to be able to essentially overcome the intermolecular force holding them together. And we'll just wind up with more of that substance in the gas phase. So with it here, if we look at the dotted line, we can think of that as kind of the amount of energy needed to be overcome in order to break those intermolecular forces, have this substance go to the gas phase. And then each of these curves is representing the distribution of a sample in terms of its kinetic energy at different temperatures. So the blue line is going to be a lower temperature, red line is going to be a higher one. And with the higher temperature, because temperature is just a measure of average kinetic energy, with the higher temperature, now we're going to have more of those molecules with a higher energy, so more of them are going to be able to overcome that intermolecular force. More of them are then going to exist in the gas phase, and if we've got more of that substance in the gas phase, we'll just have more of it bouncing around off the container walls. So it'll just be exerting a greater force. We'll have a higher pressure, and that's why we're going to see the vapor pressure is going to increase with temperature. It's just going to have more of that substance in the gas phase, so I'll have more of a pressure there. And with it, if we look at a setup like this, so we've got the manometer that we talked about in the gas chapter. We can have it filled with mercury in this curve. And then if we put a liquid in this vessel, what we're going to see is some of this liquid is then going to move into the gas phase. And eventually, over time, we're going to have an equilibrium established. So the amount that's in the gas phase is going to move back into the liquid phase. And the amount in the liquid phase is going to be the same moving into the gas phase. Doesn't necessarily mean we'll have the same amount in both phases. It just means once we reach equilibrium, we'll have the same amount moving in both directions. So we'll have the same rate. But then based on the height difference in these 2 different parts of the curve filled with mercury, just like we talked about in chapter 10, we can then determine what the vapor pressure is of this substance. And if we look at a couple examples here, the point at which the vapor pressure equals atmospheric pressure, that's going to be the boiling point. So with atmospheric pressure, 1 atmosphere is equal to 760 torr. So that's why we've got this line going across at 760, because that just represents 1 atmosphere. So if we look at water, it's going to have a normal boiling point of 100 degrees Celsius. Ethanol, a little bit lower at about 80. diethyl ether at about 35. And the reason we see these differences is going to be the different intermolecular forces. So it's going to be easier to overcome the intermolecular forces in diethyl ether. So we're not going to need as much energy to get into the gas phase. So we can have that occur at a lower temperature. Ethanol now has a hydrogen bond in it, so it's going to be at a stronger intermolecular force. It's going to be harder to separate. So we're going to need to heat this substance up more in order to get it to the boiling point, in order to actually get those molecules to start coming apart and moving into the gas phase. And then water, kind of think about it as the HOH bond. So it's kind of got both sides of it being a hydrogen bond. So the entire atom, or entire molecule, excuse me, all three atoms can hydrogen bond. So we're going to have a stronger intermolecular attraction there still. So it's going to take even more energy in order to overcome that intermolecular force. So we're going to have to heat it up to 100 degrees. And then ethylene glycol is a couple of carbons bonded together with an oxygen and a hydrogen coming off of each end. So it'll also have two hydrogen bonds, but now it's going to have larger dispersion forces as well. So we're going to see an even stronger force with ethylene glycol. And that's why we can't even actually see what the normal boiling point is going to be for this substance. And then the last thing we'll look at is these phase diagrams. And if we look at the axes here, pressure and temperature, so this is just sort of a generic one, but we'll see a couple specific ones for substances like water and carbon dioxide. But if we look at just the general setup here, it makes sense to the order we have these different phases in. So solid to liquid to gas, because with the solids, we've got them kind of in the top left corner. And whoops, with that, we've got low temperatures and then higher pressures. So we're going to have these molecules moving slowly. We're going to have them squeezed together. So we're going to wind up with the arrangement like we see here. We're going to have that rigid sort of structure that we see with solids. And then as we either start to heat it up, so move to the right, or in some cases, just sort of decrease the pressure, we can have it change to these different phases. So as we heat it up, now we're starting to give those molecules more energy. They're going to start to sort of spread out, going to be able to flow over each other. So we'll have the liquid phase, and then the same thing still as we either heat it up further into the gas phase, or we can kind of just move down the graph, decrease that pressure, allow these molecules to spread out. And that's why we see the gases on sort of the bottom right here, because this is going to be where I'll have our higher temperatures, but our lower pressures. And like I said, this is just kind of a generic one, but we'll see a couple specific ones later on. But with these diagrams, there's a couple important parts to identify. One of them is going to be the triple point. And the reason it's called the triple point is because it's going to be right where all three of these phases meet. So if we had whatever these conditions are, so this temperature and this pressure, we could actually have whatever the substance is exist as all three phases at once. And then at the top here, we've got the critical point. So this is going to be in between sort of the liquids and the gases. But this is going to be the point where if we continue to heat this even further, we're going to wind up with a substance that we can't really distinguish between liquid and gas. And that's why if you look at the graph here, we've kind of got sort of a gradient between those two phases. So liquid is blue, gas is kind of that tan, beige color, whatever it is. And then above this critical point, we start to see the gradient, just because we're not going to be able to distinguish these two substances any further, or these two phases any further. And then in between these phases, this is going to be where we'll be able to identify the boiling point, or the melting point, the sublimation point at those given conditions. So when we say water boils at 100 degrees C, we're saying that assuming we're at 1 atmosphere of pressure. But if we change the pressure, that temperature is going to change as well. So boiling water at high altitude for cooking, the water doesn't get near quite as hot. So you've got to kind of adjust how you cook. And that's what we're going to see with any of these phase changes. So when we're looking at the liquid to gas separator, that dividing line, that's going to be representing either vaporization or condensation, depending on which direction we're going. And like I said, that's going to change with pressure. So if we have pressure here, it's going to be some temperature. But then if we increase the pressure, we're going to see that that vapor, or the boiling point, is going to increase as well. And then with the melting point, just see the same idea, but we're going to see with two different substances, water and carbon dioxide, the slope of this dividing line between the solid and liquid. That's going to give us important information about the density of these different phases. So typically we're going to see that the slope of this line is going to be positive. It's going to be going towards the top right. But we'll see with water, that's going to be the opposite. And that's going to be one of the reasons water has some unique properties. And then with the final piece here, sometimes gets overlooked because it's not nearly as common as the other two. But we can sort of skip over the liquid and go straight from solid to gas, sublimation, or vice versa, or in the reverse direction, I should say, going to be deposition. And if we look at water, one thing we can note is the critical point here is going to have very high temperatures and pressures. So 218 atmospheres. It's going to be 218 times the force pushing down that we typically experience. So it's not always 1 atmosphere, but it's usually pretty close to 1 atmosphere of pressure here in Washington. At least out in Aberdeen it is. But it can get a little bit higher, a little bit lower, but still going to need over 200 times what we're usually experiencing. And then we're also going to have a temperature of 374. But this is going to be degrees Celsius. So if we're thinking about Kelvin, we would still have to add 273 to that. So we're going to wind up with almost 650 degrees, or 650 Kelvin, excuse me. So the critical point of water is going to be extremely, extremely high. And it's going to be due to those van der Waals forces. So the strength of those intermolecular forces in water are going to be the reason that this is so high. And then also with water, what's interesting is the slope of this line. The generic one we saw before, the dividing line between liquid and solid, went to the top right, kind of. Not quite as steep as the liquid and gas, but it went to the top right. So he kind of took this and just moved it over a little bit. But with water, we see we have a negative slope here. So if we take a point, so if we take a point and put it just below the melting point, and then we keep that temperature the same, but just increase pressure, what you would normally expect if you're increasing pressure is you would force, you'd expect to get more solid. But what we're going to see with water is when we increase the pressure, we're actually going to have the substance melt. And this is going to be the reason. Second. All right, sorry, my dog was being a rascal. What was I saying? I don't remember how far I got in this, but then with this, the reason the slope is going to be important for water, or the reason it's unique for water, since it's a negative slope here, is because if we take this boiling point, or take this temperature and increase the pressure above the boiling point, or melting point in this case, excuse me, since we're going solid to liquid, if we increase the pressure, we can cross the melting point. And the reason this is going to be unique is because typically if we take something and force the molecules closer and closer together, that's going to give us a solid rather than a liquid. But this is going to be the reason that ice actually floats. So ice is going to have or solid ice is going to have a lower density than the liquid water, because we're going to be, as we increase the pressure, as we force these molecules closer and closer together, we're actually melting this substance. Whereas, erase this quick. The carbon dioxide, we're going to see just the opposite. So now if we have it right below the melting point and we increase the pressure, we're going to force carbon dioxide to be a solid, because the solid is going to be more dense than the liquid. And that's going to be what we see with most substances. So that's why any of these, or the typical phase diagrams we would see, would have a positive slope for this line. But since water is negative, the liquid's going to be more dense than the solid, and that's going to have important implications for Earth, just because it allows ice to float, of course, and then it also allows for like lakes and things. The ice is going to form on top. It's going to help sort of create a barrier for the organisms in that water. Whereas if it's the other way around, they'd be exposed to the elements, and it'd be a much harsher environment in the winter times. But then with carbon dioxide, we see the positive slope on this line. So the solid's going to be more dense than the liquid. And then also with carbon dioxide, if we look at the triple point here, 5 atmospheres of pressure, about negative 56 degrees Celsius. But if we look at this and just draw a straight line across, we can never have the liquid phase at any temperature. We can't have that liquid phase below 5 atmospheres. And that's why if you've ever worked with dry ice, it just sublimes, so it goes directly from solid to gas, because we're at 1 atmosphere of pressure, more or less. So we're not even close to the triple point there. We're not even close to being able to be, we're not even close to the conditions that could provide carbon dioxide in the liquid phase there. And then also with carbon dioxide, what we see is the critical point is going to be much, much lower than what we see with water. And if you look at it, the critical point, the pressure, about 1/3, almost exactly 1/3 what it was with water. So water was 218, and then the temperature, water was 370 something. So over 300 degrees less for the carbon dioxide. So it's going to be much easier to get that critical point. And then carbon dioxide as that supercritical fluid. So we refer to it as a fluid just because it's, we can refer to it to gases or liquids as a fluid, but supercritical because super meaning above or more, and then critical just referring to this critical point. But carbon dioxide is going to be, or can be used to extract different things like caffeine, non-polar substances, just because like's going to dissolve like. So polar dissolves, or polar extracts polar well. Non-polar will do the same with other non-polar substances. So since carbon dioxide is symmetrical, both of those carbon oxygen double bonds, the dipole of them is just going to cancel out. And that's why we have a non-polar substance with carbon dioxide.